In this video, we will look at drag forces. When a solid object tries to move through a fluid, that is a gas or a liquid, it experiences a resistive force. This is because it needs to push the fluid molecules out of the way and sometimes speed them up also a little. The direction of this drag force is in the opposite direction to the object's velocity. So we can write F drag equals minus some function of the object's speed times this unit vector v object hat. Right, so we have some function of the object speed, because in general what we see is that as speed goes up, the drag force increases. And we see that the direction of the drag force is in the opposite direction to the direction of the object's velocity. Right, so this is a unit vector pointing in the direction that the object is moving, and the minus sign says opposite direction. So we don't know in general what this function is. It is probably a fairly complicated function. But what we can do as a first guess is approximate this function using a Taylor series expansion. So we will expand f of v in a Taylor series for small v about v object equals 0. But when we say small v, what do we mean? Small compared to what? So we need another velocity scale or speed scale in this problem that we can compare v object to. Turns out there is a speed scale that we can associate with the liquid. Even if the liquid as a whole is not flowing, we can still talk about oscillations in a liquid. And the speed at which that propagates, well, that's the speed of sound. So v sound we will use to refer to the speed of sound in the liquid. Remember, the liquid as a whole is stationary. The object is moving in the liquid. V sound is the speed of sound in the liquid. And so what we are interested in is when v object is small compared to v sound. So that is, v object over v sound is much less than 1. Now this number, v object over v sound, is called the Mach number. So with regards to rockets or fighter jets, you often hear numbers like, oh, Mach 2 or Mach 3.3. So in those cases, those are objects moving through the air. So we are talking about objects moving at 2 times the speed of sound or 3.3 times the speed of sound, and so on. And the same thing applies to any fluid, including water. So to reiterate, we are going to do a Taylor expansion of f of v under the condition that v object over v sound is much less than 1 and close to 0. All right, well, Taylor series expansion. F of v is f of 0 plus the partial of f with respect to v evaluated at v equals 0 times v object plus the second derivative of f with respect to v times v squared over 2 plus, and so on and so forth. We will concentrate on just these first 3 terms. So starting with the first term, f of 0, well, if there's no movement, if the object is not moving, we don't expect there to be a drag force. After all, if it's not trying to go anywhere, there's no reason for the liquid to push it or pull it in any particular direction. And so we expect that f of 0 is just 0. So that eliminates the first term. So we will look for a linear drag term and then a quadratic drag term. In this video, we will first pursue what happens with the linear drag term. We consider a sphere of radius r moving in a viscous fluid which has a coefficient of viscosity eta at a speed v. You might consider, for example, a ball bearing falling through syrup at a constant terminal speed. So we want to get an expression for the drag force that the sphere experiences. And what we're going to do is use dimensional analysis to get a first guess. So in dimensional analysis, as you either know already or have seen in the dimensional analysis video, We start by looking at the relevant quantities and getting their dimensions. So speed is length product with time to the -1. Radius is just dimensions of length. Viscosity was Pascal seconds with the units. If we convert that into dimensions, it's mass per length per time. And for drag force, which is a force, so it's measured in newtons, we have mass times length times t to the -2. So we set up a general guess. We say that, oh, well, F drag is going to be proportional to V to the power A, R to the power B, eta to the power C. We plug in the various dimensions and we simplify the various powers, and we are going to match the powers on either side. Comparing, we get that 1 would be equal to C, 1 would be equal to A plus B minus C, and -2 would be equal to minus A minus C. So that tells us that, oh, well, C is going to be 1. That's straightforward. With that information, we find that A is also 1. And then finally, B is also 1. So we have A is 1, B is 1, C is 1, which gives us that F drag is proportional to V times R times eta. So we derive this guess using dimensional analysis. The full accurate mathematical treatment of this was performed by Stokes, and Stokes' law revealed that the drag force was given by 6 pi times eta times r times v. Right, so notice a couple of things. Interestingly, for a sphere, the drag force is just proportional to the radius. It's not proportional to the radius squared. It is, no surprise, proportional to v, and it's proportional to eta. So the greater the viscosity, the greater the drag force. It's an example of linear drag. Remember, this is only one type of drag force. There is quadratic drag force and other more complicated types. But this is a good approximation when the fluid flow is smooth and laminar. That's when viscosity has the greatest effect. Now, having said that, this drag force is not purely due to viscosity. In fact, if you go through the details of Stokes' calculation, you find that Stokes' law actually has contributions from both viscosity and pressure. And we will see why in a moment. But first, just to get a better idea of what's going on, we know that the sphere is moving through a stationary liquid, but in the frame of the sphere is stationary and the fluid is flowing around it. So from the lab perspective, the liquid is stationary and let's say the sphere is moving to the right. From the sphere's perspective, it is stationary and the liquid is moving to the left. And this is what we mean by saying that it's a smooth laminar flow. You can see that streamlines are smooth and there aren't any vortices, and they get disturbed by the fluid and then come back on the other side and rejoin. Right? An undisturbed streamline would just be going straight like that. But all these streamlines near the sphere are disturbed and then come back in. So this is the kind of thing we think of when we say that, oh, that car is very aerodynamic, or that plane or that boat is designed with very smooth curves. Right? The idea is that for smooth flow, there is very little disturbance. All right, let's look at this in a bit more detail. So this is essentially a blown up version of the previous diagram. In the reference frame of the sphere, we see that the sphere is stationary and the liquid is flowing around it. So let's see what happens. As liquid molecules approach, they are pushed out of the way by the sphere in a direction which is perpendicular to the motion of the liquid. So that is the force of the sphere on the liquid. So correspondingly, there must be a force of the liquid on the sphere. And so this is the pressure component. So we can see, for example, that as the liquids are being pushed outward, like liquid flow lines are being pushed outward like this, the force of pressure that the liquid exerts on the sphere would be inward like this, so perpendicular to the surface. So for example, let's say over here we expect that, oh yeah, there will be a bit of a push from the liquid onto the sphere like that, and similarly over here there would be a push from the liquid onto the sphere like that. And if we add those two force vectors, what we see is that the components in this direction, let's put a little axis here to make things easier, so let's say that's x and that's y, so components in the y direction will cancel out, and there will be a net force in the negative x direction. But it's not only here. Look at what happens over here. After this point, the fluid flow lines actually come back together. So what do we see? If they are returning from here to here, then there must be a force pulling them back. So now the force that the sphere exerts on the liquid is inward, like so, right? It's pulling it back in. Instead of just going in a straight line like this, it's pulling it back in. But again, if there's a force of the sphere on the liquid, then there must be a force of the liquid on the sphere. So if the force of the sphere on the liquid is pulling it back in, right, then there must be a force on the sphere from the liquid, which is pulling out like this. So all these are forces on the sphere by the liquid. So by liquid on sphere. And all these are perpendicular to the surface of contact. So these are essentially pressure contributions. And we can see that with these two forces as well, the y components are going to cancel out, and the x components are going to be in the negative x direction. So overall, there's a contribution by the pressure in the negative x direction, right? Which is, remember, the opposite direction that the sphere is actually traveling. The sphere is actually traveling to the right, but it will feel a force from the liquid to the left. So this is part of the drag force. Of course, there is not only a force component perpendicular to the surface, there's also one parallel to the surface. So as the liquid flows past the sphere, well, the sphere doesn't like to see that motion, so it exerts a force on the liquid in the opposite direction to its motion. So there'll be a force by the sphere on the liquid against the motion of the liquid. But again, by Newton's third law, there must be a force by the liquid on the sphere, which would be in the direction of the fluid's motion. So we would have a force tangent to the flow line over here and over here. And again, so this is the force by liquid on sphere. This is the parallel force. This was a perpendicular force, this was perpendicular, 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 and this is a parallel force by liquid on sphere. And again, if we add these two force vectors, we see that the y components will cancel out, but oh look, there's a surviving component in the negative x direction. So this is the viscous contribution to the force. And similarly at this part, it's still the liquid flowing past the sphere, and the sphere will try to oppose that by creating a force opposite to the flow, but by Newton's third law, there will be a force by the liquid on the sphere. So I'll just again draw these green tangent arrows here. So this is F parallel liquid on on sphere, and similarly over here. And so there's again a parallel component of the force of the liquid on the sphere and a parallel component of the force of the liquid on the sphere. And again, we see that the y components will cancel out, but there will be a net force in the negative x direction. And so both the pressure and the viscosity contribute. Actually, I believe the viscosity contributes more than the pressure, and they contribute in the negative x direction. And so they both contribute to this linear drag force on the sphere by the liquid. Now, of course, not everything is spherical in shape, so often we just reduce this to F drag is equal to minus BV, where B is some constant which depends on the shape and the viscosity and so on, and V is the velocity, and the minus sign tells us the drag force is in the opposite direction of the velocity, but it is directly proportional to the velocity, so this is the linear drag force. All right, in the next video we will look at the quadratic drag force.